In the beginning there is sand, silica sand to be exact, since it contains mainly silicon dioxide from which we extract the precious silicon. By the way, silicon is the second most common element in the Earth's crust, so we won't run out of it. Together with coal or other source of carbon, the silicon sand is melted down at over 2000 degrees Celsius. The result is metallurgical grade silicon with a purity of almost 99%. When it cools down, metallurgical grade silicon solidifies into a shiny crystal such as these.
Metallurgical grade silicon can be made of nearly any kind of sand. Still, it makes sense to use very pure materials. Herewith, a purity of already 99% may be reached. To produce it, the silica sand is put in a furnace together with a source of carbon. This alloy is melted down at 2000 degrees using an electric arc. In this process, the oxygen and silicon bonds are broken and carbon dioxide and the silicon that we want to extract are formed.
Silicon is extracted from quartz sand. For use in the photovoltaics industry, the semi-metal must be 99.99% pure. To generate solar power, the photovoltaics industry utilizes the semiconducting properties of silicon. In special ovens, raw silicon is melted at temperatures of over 1400 degrees centigrade. A thin rod, known as the seed crystal, is then submerged into the liquid raw silicon and pulled back up very slowly. At this step in the process, the liquid silicon accumulates on the seed crystal and solidifies. Over 4 days, a silicon rod of up to 2.8 meters length takes shape. This basic round crystal, known as an ingot, is now cut into a rectangular shape. This is done for purely practical reasons. Later on, square-shaped solar cells can be installed much more effectively on the surface of a solar module. The ingots are cut into millimeter-thin slices using a very fine wire saw. The individual slices are called wafers and form the basis of each solar cell. Once the wafers have been cut, they are sent through a wash tunnel. This is because even the smallest piece of dust or dirt can compromise solar cell production. The wafer's surface is now very flat. Just like a mirror, many rays of light are reflected and can no longer be used to generate power. To prevent this reflection, the surface is etched and roughened in a chemical bath. If the cells are put under a microscope, one can see the resulting pyramid structure. With this fine pyramid structure, light is refracted multiple times, allowing incoming light to be used far more effectively. The next step in solar cell production is diffusion. Here, a negatively charged phosphorus layer is added to each wafer's positively charged layer. In an oven heated to some 900 degrees centigrade, phosphorus atoms are injected with the help of nitrogen. The gaseous phosphorus-nitrogen mix is deposited on the wafer. At the interface between positive and negative charge layers, the free charge carriers created by the light are released. This generates an electric current. But how is the power that is generated in the individual cells transported? A stamp presses a silver alloy onto the front of the cells. This creates the typical grid pattern. This silver coating ensures that the power can be transported later on. The solar cells are now complete. They can generate and transfer power. But each cell has a different level of electrical conductivity. In a series of tests, the cell's conductivity is evaluated and sorted.